All right, so this week's lab is on Faraday's law. Before I get too into that, let me just give some general announcements. We're getting near to the end of the semester. I'd say there's probably about three or so labs left. So you're going to go ahead, make sure that you get all the points you can for all the labs that are left. Um, it's just going to be an average of all the points that you've earned throughout the semester. And the quizzes are going to be 30%. Um, and a reminder, the quizzes are uh, there's going to be one that is the lowest that will be dropped. Let me start sharing the screen. Oh, and next week is spring break, so no lab next week. Let me share my screen. We're not there yet. Lab 9, Faraday's Law. When we go into the instructions, we'll see pretty much, the pre-lab covered most of this already. Let me go over this as well. You can put your own introduction right here at the top. And what we're going to be doing is pretty much the same as always, following along step by step. Something different about these instructions are that I've placed the point values on each part. So you can see this first part is worth 16 points. We go down for a little bit. So this next part, 4 points. And last one is worth 20. So let me know what you think about that. Also, like points on each individual thing. So up at the top, your own introduction. In the simulation, we go to PhET simulation. That's going to be this you saw. We're going to be manipulating this magnet around this coil of wire. So let's put that right there for right now. For this first part, we're only going to be moving the magnet, around the outside and up to where the north side, the north pole of the magnet, here it is. The north pole of the magnet is right inside the middle. So best judgment, where do you think the middle is? Kind of right here. It's kind of three-dimensional looking. Okay, so very qualitative lab. You have these two boxes to check. I'd go ahead and check both of those. So you can see the magnetic field around the magnet. That's permanent. It's not going to change around the magnet. You can see the magnetic field lines that come off of the magnet. And what we're going to be doing is, saying like whether something is increasing or decreasing. Make sure to always state like a direction. It might ask, what is the direction of the flux pointing? And so I'll get to that in a minute, but that'll be, in this case, it's pointing into the coil because the lines will be coming out, magnetic field lines are coming out, and they are entering this sort of coil cross section. Okay, so that's going to be, largely what we're going to be doing. It's qualitative today. Okay, so first part is just very simple, and it'll say to like move it slowly, quickly, and you slowly versus quickly, and you'll say what you see happening. Next part, we're going to be putting it all the way through and also flipping the magnet while it's inside the middle of the coil. So I'm going to do it while it's over here, and I'm going to turn these off so I don't ruin anything or I don't spoil anything. So while the magnet's out here, if you press this button down at the bottom, it will very quickly, instantaneously flip it around. So it's, imagine you just sort of spinning it and it's upside down and then flips it again. So very simple tools to go about this part 1 and part 2. Part 3, I have this sort of highlighted bit, so you can make sure to read that. There isn't going to be like a conclusion at the end. This whole part 3 will count as your conclusion. So I guess you could think of this first question as kind of, basic sort of wrap up. It's only worth 2 points. The large, point value is going to this 3.2. And that's kind of like your own little research paper type thing, research and I guess persuasive essay. So you're going to look up a few different ways to store electricity. And you're going to try to convince the reader, you're going to try to persuade the reader that your choice is the best of 3. So you're going to look up methods to store electricity for like a small town, and you're going to try to convince someone, not me. You think of someone who maybe isn't familiar with what's happening. So try to walk them through what energy storage is, what it's doing, and consider cost, convenience, your own opinion. Just make sure it's a well-written little essay bit. So I'd say paragraph to a couple paragraphs. I think a paragraph is a bit short. Maybe insert your paragraph. Okay, so maybe if it's a good paragraph. Then you're going to take that, your writing for this one, and you're going to go to this website right here, prowritingaid.com, and you're going to sort of see how your writing style is analyzed and judged. So it doesn't matter what the score says right here. It's just you just have to insert your screen capture, and then the screen capture of your summary page. And so what's going to do is it's going to tell you how you can improve your writing. I know it's getting near the end of the semester. There might be a lot of writing in a lot of other classes. You can use this to see how to write a higher quality paper. So then you're going to, at the very end, use the hints and tips that it gives and try to improve your own paragraph that you wrote up here for 3.2. So you don't have to fix, I have it right here, you don't have to fix every single problem, but it should be significantly better. So generate a significant improvement. Okay, and then insert a screen capture of that page. All right, and of course at the end, make sure you fill out the evaluation of the instructions. And yeah, so are there any questions on the lab or this procedure?
We're still writing an introduction, right?
Introduction at the top, yeah. So just very brief thing on Faraday's law. Let's see. I think the only, from another class, something that is worth mentioning. If you're going to find, sources, you can just put like if you're going to have sources for this part, you could put like the URL, where you found what you're mentioning, and you just put that underneath the paragraph in this section. So I can go in and see where you're getting your information from. You don't have to make a full works cited at the end. Okay. So this is a experimental lab, and that it's a bit different than a few before, but hopefully it'll help. Okay, let me go over to not that. Let me go over to the notes. Okay. All right. So today, the simulation we're going over is Faraday's law. And this is right at the sort of the peak of what is difficult and complex for electromagnetism. So I'll try to explain the best I can. Let's first start with a definition for Faraday's law. Faraday's law states that a changing magnetic field will induce an EMF in a loop of wire. Electromotive force, I could just say current, but EMF is a bit more technically correct. EMF in a loop of wire. So that's going right to the heart of what we're learning today. So a changing magnetic field will induce a current in a loop of wire. Let me sort of draw a little diagram. This is not, usually I do diagrams that help. This is just sort of a display. You don't have to draw this one. But Michael Faraday, he was an experimental physicist who was really good at understanding, how to set up an experiment. And they wanted to figure out in the 1800s, from last week's lab, we learned that if we change the current going through a wire, if we made the current stronger, there'd be this stronger magnetic field that'd be produced. So we went from current to magnetic field. People in the 1800s were wondering, can we go from magnetic field back to current? Does it work both ways? And so people would, try out their own little experiments, but it wouldn't go that well. It wasn't until Michael Faraday came in with his own design. I'm just going to make it really rough sketch of what it looked like. Let's go like this. That's a switch. And what he did was he had a battery that was hooked up to a coil of wire. And that coil of wire, let's put like a V right there. That coil of wire, he knew, would make a magnetic field. Let's say it would be like going through like that. Magnetic field would be produced by this coil of wire once the circuit was closed. Once we close this switch, that magnetic field would sort of be created. And so what he wanted to find out was, if you do this, would this one that's right next to it also get a magnetic field that's produced, since it's so close, it's being affected by it? Well, what would happen is right when he'd turn it on, so right when he'd close the switch, that field would go, and then just for a split second, right when he turned it on, this one over here would have a little bit of magnetic field being produced. So a little bit of current being induced, but then it would go away. And then let's go like that. And then he'd turn it off. He'd open the switch. He says, I wonder what happened. It didn't keep going. So he turned it off. And just for that split second, right when he turned it off, then there was another magnetic field being produced. And since he was very good at sort of, focusing on what was happening, he concluded that's a changing magnetic field will induce a current in a wire. So it was the act of the magnetic field changing. So let's go on to I'll go on to another another related example. Let's go to flux. So just general, no, I'll say magnetic flux. I'm going to define this. Magnetic flux is, I can define as the amount of magnetic field field lines that flow through a specific area. Okay. So this is going to help us sort of understand and visualize some of what's happening up here. This is a very just demonstrative picture. Okay, so I'm going to go to a different page. I'll come back to this page in a moment. Okay, so say we have just a field of parallel, or I guess, parallel magnetic field lines, and they're all going the same direction. How can we think of flux something that's going through it. Let me make a shape that will help us sort of visualize. Imagine this as like a river. You know, when I first learned this, the teacher described it as a river, and you're like throwing a net over the middle of it, and trying to see how much water would go through the net. So let me, that's, and I don't know, I don't like that. Make it like blue. Okay, so this blue line, this blue rectangle is representing sort of like a net that's going across this, field of parallel lines. Since it's so large, it's containing 1, 2, 3, 4, 5, 6, 7 magnetic field lines. So it has a set number of magnetic field lines going in it. If I move it over, it still has 7 field lines in it. If I move it up here, it still has 7 lines going through it. If I move it down here, still has 7. So there's no change however I orient this. So there's no change in how much is going through it. There's a specific amount of flux. So just this flow through this net, sort of draped across this river. So it's, good, or I guess easy to assume we can make a different case. So what if I had a net that's this big? Again, blue. Okay. So, nope. Now I'm just making a mess. So we have this. It's a much smaller net. So it's a smaller, flux area. It's going to have less lines passing through it. Okay, what if we, move that around? It'll always have 3. So 1, 2, 3, move it around, still has 3. Like that. What is the case where there is a changing flux? Well, I can rotate this big one. So what if I rotate it like that? So it had 7 before. Now it only has 3 passing through it. So it has less. So the magnetic flux has decreased. And if it's completely, parallel, there's 0. So this idea of magnetic flux, we are making this sort of area, and we're observing how many field lines pass through that area. In this case, it's 0. Let me make let me add the equation that goes along with this. We're not using this equation, so don't worry. But the magnetic flux is represented with a phi, or I guess phi, this capital Greek letter, B for magnetic flux, is equal to the strength of the magnetic field times the area of your flux surface, so just sort of that cross-sectional area, times whatever angle you have it rotated at. You see if it's at this angle. I'm going to add more lines. It's going to mess it up, but You see that's 90 degrees. Cosine of 90 degrees, 0. So there's 0 flux going through that. Okay. Don't want to add too many lines, make it messy. All right, so we have this general idea of flux is a surface that things pass through. Now, let's look at this idea of flux with our bar magnets. Now, we're using a bar magnet. The original, Michael Faraday's used, 2 different, current carrying wires. We're just using this magnet for our lab today. What do I want to do? I want to do this. I'm going to make another one of these. It's going to mess up thing. That's blue. Okay, so here is our, let's say this flux surface is our coil of wire. So this is like big net. How can I, like that? Okay, so this is looking like directly from the side, but this is the very center of a large coil of wire. That's like that. Okay, so we're looking at it directly at the side. So that's our flux surface right in the middle. Now, when in our lab, we're moving the magnet. In my example, I'm moving the coil. But you see as it gets a bit closer, now there are 2 magnetic field lines that are passing through this flux surface. So it went from 0 out here to 2 that are passing through. So that is an increase in flux passing through this loop. Let me help this, settle in with, a front view. If we have, that's what I should have put. I need to put, if this is our eye, and we're looking that way, we can see this coil head on down here. So we see the coil, and as we push this magnet closer in, now there are these 2 magnetic field lines entering the coil. So let me represent those as, they're lines going away from us, so they're X's. Like that. Okay. What else is going to happen? Well, since there's this change in magnetic flux through this loop, we need to, let me go back to that other page and define Lenz's law. And if you aren't catching up with this, I'm going to try to combine this all in one page later on the notes. Oh no, where'd it go? Down here maybe? It's right here. I have too many things. Okay. Lenz's law. law states that the magnetic field magnetic field formed by an induced current will oppose the change in magnetic flux. Okay. So we have this coil of wire that originally has a certain amount of flux going through it at any given time. So when it was just sitting there by itself, it was 0. But then we introduce a magnet. We get a magnet near it. So there's this change in magnetic flux. And the wire, you can think of it as having a mind of its own, but it's just a conservation of energy. The wire doesn't like that. So it will create a magnetic field. It will create a magnetic field that will try to oppose this change in magnetic field or change in magnetic flux. Okay, I gotta get all my pictures back. So I think that's the last definition. So we'll be on the other page from now on. That's up. They're all in pieces. Okay, that should be it. I'll do the rest on this one. Okay, so as we see right here, yeah, we'll go like that. As we get that magnet closer, there's this change, there's this increase. Now there's 2 magnetic field lines going through the coil where there was originally 0. So the coil doesn't like that. It wants to oppose this change. So it's going to create its own magnetic field that opposes these. So which direction would it have to go? Would it have to point to oppose it? It'd have to be completely opposite. It'd have to be towards us. So it's going to create these 2 magnetic fields that point outward towards us. So it's going to do that by inducing a current in the wire. And in order to get one that's, in order to get a magnetic field that points towards us, use the right-hand rule. So I'm going to, you can use your thumb as the current, and whichever way your fingers curl, that's the magnetic field. So in order to get, my fingers pointing at me, I have to make a current that goes clockwise. Like that. So the wire is inducing a current that's the red. It's inducing this current just so it can make this magnetic field, these 2 dots, induced magnetic field, that opposes the change. If I go from here, 2, and then 4, you can see now that's just increasing. The magnet is getting closer. So the wire is going to keep inducing that current to try to oppose this change. So instead of 2, now it's 4. That's. I got way too many layers. That's. Now there are 4. And so the, I think we might be able to see it now. So it's going to keep inducing a current that will make a magnetic field that opposes. And I would do the 6, but I feel it might be overkill at this point. Let's say I stop right here. Let's say I stop right here, and I'm no longer changing the magnetic field, and the magnet stays at this distance. Okay, so there are 4 magnetic field lines that pass through, and there's no more change in flux going through that surface. Okay, so then what if I take that magnet, or I move the coil farther away, and I move it out like that? So then it went from 4 going through down to 2. Let me draw that. So the black writing, that's the actual. So then it went from 4 and it's decreasing. It's decreasing down to 2. 4 and it's decreasing. I need to make this other one over here. It went from 4 down to 2. The magnetic, the coil of wire, again, doesn't like a change in flux. So once it stopped, it was fine where it was, but then I'm changing it again. It doesn't like change. It's going to resist whichever direction I change. So I am now having less magnetic field lines go through it. I went from 4 to 2. And so the coil is going to try to induce a current that resists the change in flux. Go like that, go like that. So it used to have 4, and it doesn't want to change, so it's going to try to have 4 again. So it's going to induce a current that's pointed that way. You think of up here, these were trying to cancel out the change. That's why they were even numbered and oppositely signed. Down here, it stopped at 4 and it wants to go back to 4. So it's trying to add its own magnetic field to it. And so going in using the right-hand rule, the current direction is now going this way of the induced current, because it doesn't like change and it wanted it how it was over here with 4. Okay, so hopefully, I think I did, I think that's pretty good. I'm not going to do the 6 example. So you just ignore these two over here. Are there any questions on, any of these notes? I can go back to the definitions if you want. But later on, I'm going to try to put like all these pictures and those definitions on the same page. Let's see, what am I doing today? I don't think I'm looking for anything today. It's a real short lab. It's qualitative. So I'm going to say I'm not looking for anything. I will let you guys go if you want to leave. If you want to stay and work on it, that's good too. You can finish it out right now, so you don't have to do anything over, the rest of the week, and we'll have a good spring break. A good start at least. So let me get the rooms open. All right, so the rooms are open. I'll be right here if you guys have questions. If you're just gonna head out, have a good spring break, and if you have questions, you can email me. And yeah, I think that's it.